Hello everyone. Today we're going to continue with our discussion, and today it will be the first session that we will be moving further in our pre-processing steps. So if we look at our CFD process again, just to remind you where we are in the bigger picture of the things. If you remember, we talked about geometry modeling, the negative geometry and how it works, how we should create our geometry, how it differs from the real geometry, and how we can minimize the size of our geometry. The second step was our basically mesh generation, which was, if you remember, we have one big control volume, but since we have developed our equations based on assumption of infinite small differential size control volumes, now we have to divide our big control volume to small pieces, smaller control volumes, differential size control volumes, which we call them cells, then solve our equations over every single one of those cells. So we covered these two steps. Now we are moving to our next step, which is basically preparation of our simulation, and by the end of today you basically will be able to perform simple laminar simulations. So before we dive into the simulation part, we have to also cover an essential part, which are our boundary conditions. Why do we need boundary conditions? Why to solve for our unknown parameters in our system we need boundary condition? There are two explanations for that. One is the physical explanation and the other is the mathematical explanation of it. The physical explanation is quite simple and you can relate to it. For example, you have a room and you want to find out the temperature distribution inside that room. You want to see what are the temperatures in different locations inside the room. Essentially, physically speaking, you cannot find the distribution without knowing what's happening on the walls of that room. You want to know that what are the temperatures of the walls, whether the walls are insulated or they can transfer heat to the outside. And if they transfer heat to the outside, what are the temperatures outside? What are the conditions of the temperature outside? So this means physically you need to know the physical conditions surrounding your control volume. Mathematically speaking, there's also a good reason for boundary conditions. If you recall, we have 5 unknowns in our system. We have 3 velocities, we have pressure, and we have temperature. To solve these 5 unknowns, mathematically, you require 5 equations. Those equations were the continuity or conservation of mass, 3 Navier-Stokes equation in x, y, and z directions, which we also call them Navier-Stokes equations, and the last equation that you need is the energy equation. Okay, so when I'm solving for 5 equations with 5 unknowns, a critical part of the mathematical process are the constants in those equations, because remember, these are general equations, right? In order to find definite answer, definite result to them in definite cases, you need constants in those equations. Those constants are actually your boundary conditions. For these reasons, before moving further away to our simulation, we have to discuss that what are the boundary conditions in our CFD simulations and how do we define them. So boundary conditions, basically, as we said, the necessity of them are to apply external condition on your solutions. The procedure for defining boundary conditions is twofold. First, you have to identify the boundary locations. Okay, and the boundary locations are basically the surfaces encircling your control volume. That's kind of an easy part. The second part of it is, okay, now I know where are the boundaries. Now I have to basically supply information at those boundaries, the required information, the velocity information, temperature information, mass flow information, so on and so forth. So the required data on boundary conditions are: one, your boundary condition type, which means, okay, what kind of boundary I am talking about. Am I talking about the wall boundary, velocity boundary, or other types? Second, physical models employed in that boundary. Okay, so what equations am I solving in my system? So if I'm solving, for example, whatever equation I'm solving, I have to provide corresponding related boundary conditions for that equations. Okay, so, and remember, poorly defined boundary condition can greatly impact your solution. So always and always remember this. The errors, one big source of errors in your system are errors in defining your boundary conditions, because most often your boundaries have some sort of velocity inlet or pressure inlet or mass flow inlet element in them, and whatever error you create in those will basically carry it out throughout your simulation. Now, in terms of defining the type of the boundary that we have, we basically define them in two ways. They are same boundary conditions, but we are defining them in two different ways. Number one, we are defining them mathematically. In terms of mathematics, we have three types of boundary conditions. We have Neumann boundary condition, we have Dirichlet boundary condition, and we have mixed boundary condition. Now let's look at them, see what they are. The Dirichlet boundary condition is a constant value of a variable at the boundary. So for example, if you define constant velocity at the boundary, if you define constant pressure at the boundary, if you define constant temperature at the boundary, mathematically speaking, they are all Dirichlet boundary condition. The second is the Neumann boundary condition. In Neumann boundary condition, it is the constant value of the gradient normal to the boundary. So this time, we are not per se dealing with the parameter itself. We are dealing with its gradient, with its rate of change. So if the rate of change, the derivative of the boundary is constant, this is called Neumann boundary condition. For example, if you have constant heat flux from one of your walls in your system, that's basically delta T over delta X equal to a constant. That's a Neumann boundary condition. The third type that you have is called mixed boundary condition. Mix, as you can see the equation in here, is basically a mixture of your Dirichlet boundary condition and Neumann boundary condition. This basically covers everything, every other type of boundary condition. Although the majority of the boundaries that you will be dealing with them would be one of the either Dirichlet boundary condition Neumann boundary condition. But in complex systems, in complex boundaries, you also will be dealing with mixed boundary condition. Now, the mathematical type of boundary conditions are useful when you want to write your own CFD code, or you are dealing with an open source CFD code like Kiva, like OpenFOAM, that you have access to the source code and you want to change boundary condition. That's when you go through the mathematical definition of the boundary condition. But for us in this class, since we are dealing with applied CFD, which means we're not going to write our own code. We are using softwares, commercial softwares, to solve for our equation. We use another type of classification, or you might call them definition for boundary condition. This is rather a physical definition. So the previous one was mathematical definition, and this one is basically a physical definition of boundary condition. There are three major categories of boundary conditions when we define them as in terms of their physics. One is external boundary condition, the second is internal boundary condition, and the third is cell zones or continuum boundary conditions. Now we will go through one by one, see what everyone what they mean and where the applications are for us. In external boundary conditions are the boundary conditions that are in the surrounding of your system, where your control volume finishes. So that's basically the actual boundary between your system and the outside world. The internal boundaries, on the contrary, they are inside your control volume. You might say, why do we have boundaries inside the control volume? There are many applications for them, which we'll be seeing today in our discussion. The last one are the cell zones, which cell zones are a specific type of boundaries. They are named actually some sort of boundaries, but they are not actually boundaries. They are attributes of certain number of cells in the volume of your control volume, which you will be seeing what they mean in our coming slides. So let's start with the important ones, the flow inlets and outlets. Basically, a wide range of boundary condition types lets the flow to enter or exit your system. So, and this is very common boundary condition, because most often you have some sort of flow coming into the system or going out of the system. So, generally speaking, these boundary conditions are pressure inlet and pressure outlet, regardless of the type of the flow that you have. If you are dealing with incompressible flow, which means the density is constant, density is not changing, you are dealing with two types, velocity inlet and outflow boundaries. So pressure inlet and pressure outlet can be used with any sort of flow, regardless of whether it is incompressible or compressible. Velocity inlet and outflow are basically specific to incompressible flows, and mass flow inlet and pressure far field can be used for compressible flows. So first, the velocity inlet. In velocity inlet, basically you are defining that the flow which is coming into your system, which is coming into your control volume, it comes with what sort of velocity. And remember, velocity is a vector, and scalar properties of flow at the inlet boundaries will be defined. So this is intended for incompressible flows, because remember, velocity inlet flow is useful only if you have incompressible flow. The reason for that is that, to tell you the truth, the only real boundary condition at the inlet that you have is mass flow, because the only real physical thing that is going into your system or coming out of your system is mass, nothing else. Now mass, m dot, is equal to your density multiplied by your cross-section A multiplied by your velocity. So m dot is rho AV. Okay. Now, if my density is constant, which means if it is incompressible, and of course my area, cross-section area of the inlet is constant as well, so might as well I define velocity at the inlet instead of mass flow. Okay, so since m dot is rho AV and rho and A are constant, instead of defining m dot, I define V. But remember, if you go to compressible flows, that's not correct anymore because your rho, your density, is changing as well. So let's see how we can define velocity inlet in our answers. There are different specification methods. There is magnitude and normal to the boundary. There is components, and there is magnitude and direction. So the way it works, if you choose the first one, you just provide the quantity of the velocity, like 2 meters per second, 3 meters per second, and the system will apply that normal to your velocity boundary, whatever the orientation of the boundary is. In component, you provide the x, y, z components of the inlet velocity, and in the last one, you provide the magnitude, 2 meters, 3 meters per second, and also the direction vector. The most common one to use is the first one, since you do not need to be worried about the orientation of the velocity inlet surface, and you just provide the magnitude. Now, you can provide uniform velocity, so you can provide constant velocity. You can provide a file which is basically the coordinates of different points at your inlet with associated velocities. This is mostly useful for simulating an experiment. So when you are dealing with an experiment, most often you have a collection of inlet velocities at different points of your inlet. That's when you use the profile. The last one, which is called UDF, or user-defined functions, which will be discussing that comprehensively in our last subject of the semester. You basically provide equations for velocity inlet at the boundary. So the next one is your pressure boundary condition. So in pressure boundary condition, you provide the pressure at the inlet or at the outlet. The only thing that you have to be careful about pressure boundary condition is the definition of the pressure. So in its definition, you have one absolute pressure which is compared to zero vacuum pressure. That pressure equals to your static pressure or gauge pressure, so static or gauge, plus the operating pressure, which is usually your environment pressure. For example, if I have a pipe in an environment which is the pressure of the environment is 1 atmosphere or 100 megapascals, okay, and I say, okay, the flow enters the system with 2 megapascal pressure, it means the static P. It means I'm talking about this part, the gauge pressure. It means 2 megapascal in addition to the environment pressure. Okay, so that's the gauge pressure. So this is not actually something new. You already knew this from your thermodynamics course and fluid mechanics course, but I mentioned it here just to be careful about it. So the total gauge pressure at the inlet, basically, so remember here we were talking about the type of pressures. Now we say, okay, you always provide the gauge pressure. Now to provide the gauge pressure itself is basically categorized in two different equations. If you're dealing with incompressible flow, which is the subject of our class throughout the semester, we will not be dealing with any sort of compressible flow. So in incompressible flows, your pressure has two parts. The static pressure, which comes from the weight of the flow basically, and a second part which is the dynamic pressure, which is the pressure created because of the velocity in your system. So in your incompressible flow, you have a total pressure which is the summation of your static pressure and your dynamic pressure. In compressible flow, it's a bit more complex. Basically, you are dealing with a static pressure with this equation, which relates to the specific heat and also the Mach number. And you know what the Mach number is, right? Mach number is the velocity of your velocity divided by velocity of the sound in that medium. Okay, so if Mach is more than 1, basically you're talking about supersonic flow. If it is around 1, you're talking about sonic flows. And if it is less than 1, you're talking about subsonic flows. But for us, as far as we are concerned in this class, we are dealing with this equation, which is incompressible flows. For pressure inlet, the way we assign it in ANSYS is basically you provide the gauge total pressure in here, and just ignore this part. This is if you have turbulence. So it's very simple. You provide the gauge inlet pressure at your inlet boundary condition. For pressure outlet, basically you define, usually you put it 0, because usually our gauge pressure at the outlet is 0. So you just basically provide 0 gauge pressure at the outlet, unless there are specific situations where you need to provide another pressure. The only thing that you have to be careful about in pressure outlet is something called backflow. So what the backflow is, imagine a pipe. Sometimes for some reason, mostly geometrical reasons, like the geometry of your pipe has a step near the outlet or so on, many other examples. At some parts of your outlet, the flow comes in instead of going out. For example, imagine you have a flow circulation near the outlet at some point. So, and some part of that flow circulation causes the flow to come in from the outlet. This is not something out of ordinary. It happens a lot. For that reason, you need to define a backflow pressure at your outlet boundary. Why? Because remember, the flow of information is from inside the pipe to the outside. So all the downstream cells, they get their information from upstream cells because the flow is coming from upstream to the downstream. Now imagine at the outlet, at some parts, the flow goes the other way. It comes from upstream, from outside to the inside. So you need to provide some information from the outside to the solution to be complete. Now, for backflow pressure, you don't need to provide exact numbers. It has to be a very good guesstimate, basically engineering estimate. So that's the only part you have to be careful about. So this is how the pressure outlet looks. You basically provide the gauge pressure, and here the backflow parameters that you have to provide. So remember, at the backflow, you basically provide here backflow. You basically provide the information that is you think that's. For example, if the pipe, it is a pipe, it's exiting to the atmospheric flow outside, so the backflow pressure would be 0, the gauge pressure would be 0. So as long as you provide some sort of educated information for the backflow quantities, that would be fine. So the next type of the boundary is called outflow boundary condition. So basically in outflow boundary conditions, what we have is you don't have enough information from what the outside of your outlet boundary is. So the outflow boundary condition is used basically when you don't have information about the outside of your control volume. In this case, basically the solver extrapolates the required information from interior. So what it does is basically zero gradient of pressure at the outlet. Basically, imagine the last two layers of the cells at the outlet of your control volume. It will assume whatever pressure is at the inner layer is equal to whatever it is at the outer layer. So basically, it assumes zero gradient at the pressure. This is not a very desirable boundary condition, but nonetheless, you can use it whenever you don't have information about the outside. There are some restrictions on the outflow boundary condition. You cannot use it with compressible flow, and you cannot use it with pressure inlet boundary condition. These are the two most common mistakes people make. So remember, do not use it with compressible flow and do not use it with pressure inlet boundary conditions. The next one is your mass flow inlet. So basically in mass flow inlet, you provide the mass flow. Instead of providing the pressure, instead of providing the velocity inlet, you're directly providing the mass flow inlet at your boundary condition. It is very useful for compressible flows, and the information you provide are basically your mass flow inlet, your initial gauge pressure, if you have an initial gauge pressure, your temperature, and direction specification method, whether you're providing components or normal to the boundary, so on and so forth. So this method is recommended to be used for compressible flows. For incompressible flows, always try to use a velocity inlet. The reason for that is when you are dealing with an incompressible flow, what happens is since the density and the cross section is constant and you go with mass flow inlet, the only thing you are doing, you're putting an extra calculation on the shoulder of the software, because all the software has to do is divide the mass flow by your constant density and your constant area cross section to come up with the velocity at the inlet. Because remember, your unknowns are velocity, not the mass flow at your control volume. So your boundaries has to be in terms of your unknowns. But you can by all means put this calculation on the software. But remember, since the software does calculations using numerical methods, you are adding an unnecessary basically error into your calculation. So it's always better if you even have the mass flow inlet as your input property, just do a hand calculation and calculate the velocity inlet and provide that to the software. The next type, and which is arguably the most common, most useful, most used type of boundary condition, is the wall boundary condition. So in wall boundary condition, basically you're providing two types of information. You're providing momentum conditions and you're providing thermal conditions. So there are two types of conditions you're providing at the wall. So at the wall, you're providing whether what happens to the velocity at the wall. There are two cases for velocity at the wall that you can provide, and actually three cases, but we're putting it in two categories. So in three cases the three cases are basically no shear stress, no slip condition, which means the velocity of the flow on the wall is 0. That's a common wall. That's most common way of defining a wall. So the velocity of the flow on the wall is 0. That is in one side of the extreme. The other side of the extreme is, spectrum is free slip condition. In free slip condition, what happens is whatever velocity you have on the inside the flow, that would be the same on the wall. In this case, the wall basically does not slow down your velocity. All it does, it avoids vertical velocity, meaning it avoids your flow to pass through the wall. Remember this, no matter what type of viscous condition you put on the wall, always and always the normal velocity on the wall is 0, meaning the flow cannot pass through the wall unless that's a porous medium, porous wall, which is another type of boundary which we will be discussing in a moment. So between no slip condition, which is 0 velocity on the wall, and free slip condition, which is the velocity of the flow, free velocity of the flow on the wall, there's something called shear stress, specific shear, meaning you're providing specific shear on the wall, which means you're not going with 0 velocity, you're not going with free slip, but you're going with a specific type of a slowdown on the wall. So you're not saying the velocity on the wall is 0, and you're not saying it goes with free velocity, but you're saying for whatever reason, mostly coating in physical world, the velocity slows down, but it doesn't get 0. So these are the three basically viscous condition that you provide on the wall. The next type of condition that you have to provide on the wall are the thermal condition. That's in a case that you're solving for energy equation, in a case that you are solving for temperature on the wall. There are several types of thermal boundary conditions on the wall, but most commonly you provide either constant temperature on the wall or you provide heat flux on the wall. Now if you provide a heat flux on the wall, it's either constant heat flux or it's 0 heat flux, which is an insulated wall. But remember, you provide thermal boundary conditions if and only if you're solving for energy equation. Otherwise, the only conditions you will provide are the viscous conditions on the wall. The next type of boundary condition is periodic boundary condition. Periodic boundary condition is not very common, and the purpose of it is actually to minimize your solution. So what that means is, basically, if you remember, our rule of thumb in CFD was basically to reduce the size of your simulation as much as possible. So meaning decrease the size of the geometry as much as possible. The periodic boundary conditions are the best way of doing that, but given the right condition. So they are used when the following have a periodically repeating nature. So if your system has some sort of periodically repeating nature, you can use periodic boundary condition. That's, for example, physical geometry. If your physical geometry is repeating, if your flow pattern is repeating, or your thermal solution is repeating. So something is repeating in your system that you can use periodic boundary condition to reduce the size of your simulation. Now there are two types of periodic boundary condition. One is called delta P0, which means your delta P, the change of pressure across periodic planes, are 0. The second one is that the delta P is not 0, but it's changing with a definite number between periodic planes. Now let's look at what that means. So here I've given you two basically common example. In here, What you have arrays of pipes. So the circles are the pipes, and assume they are 3D pipes going into the plane. So this is your basically y direction, and this is your x direction, and the z direction goes into the plane. Now you see this is a sort of geometry repeating itself. Your pipes, every 3 pipes on top of each other, is identical to the next 3, identical to the next 3. The only difference between these set of trees is that the pressure is dropping. So the pressure is changing by a constant number between each section. Now, for us, instead of solving for the whole thing, we will take one section, and the blue lines would be our periodic boundaries. So we will only solve for this part and using periodic boundary conditions. And if we do that, it is as if we have solved for the whole 9 pipes. So in this case, you see we are reducing the geometry significantly, going from 9 pipes to only 3 pipes. Another example for where the delta P is 0. Here you have a swirl flow. So the flow goes down in a vertex format down a tank, for example. If you look from the top, so if you look from here, this is what you're going to see. You're going to see a circle, that flow is circling inside. But if you only take a quarter of the circle, so instead of taking the whole thing, I take only the quarter of the thing, the other quarters are exactly the same, and even the pressure doesn't change. So instead of simulating the whole thing, I will take a quarter of it, define this as wall as it is, and define these 2 hashed lines, the hashed green lines, as my periodic boundary condition. If I do that, essentially, instead of solving the whole thing, I'm solving for only a quarter of it, reducing the size of my simulation significantly less. So we talked about different boundary conditions and basically the types of different boundary conditions, but we have to also talk about proper specification of boundary condition. This is basically regardless of what type of boundary condition you're using, there are some underlying assumptions that has to be abided by to have proper boundary conditions. Number 1 rule in defining boundary condition is to be careful about over-specification and under-specification. So imagine you have a control volume, it's a complex geometry, and you are dealing maybe with 20, 30, 40, even 100 different boundary conditions. Now, over-specification, what happens in over-specification is you provide 2 or more types of boundary condition to a single surface. So a single surface is both, for example, wall and inlet velocity. That's called over-specification. In under-specification, you forget to provide a type for a surface which is a boundary. So, for example, in over-specification, you have 20 surfaces that are your boundaries. You have provided 22 types, more than number of surfaces. In under-specification, you have 20 surfaces that has to be provided with boundary condition. You have provided 18, 19, which leaves basically 1 surface without any type. Now, dealing with our software, dealing with over-specification is different from dealing with under-specification. So in over-specification, if you over-specify, the software will give you an error saying you have over-specified. It won't unfortunately tell where the over-specification is, but it will tell you it's over specification, and you literally has to go you literally have to go through your geometry and boundary condition to find out that over specification. Now the way software deals with under specification is quite different. In under specification, what it doesn't give any error to you, but what it does, it looks at the neighboring boundaries, and through its automation it guesses the best type of boundary for that single surface. So for example, if you have forgotten to provide boundary condition for a surface and their surrounding are all wall types, this one will automatically be assigned as wall. This is both good and bad. Good in terms of that it will take care of under specification by itself, but the bad point is, the negative point is, it might provide the wrong type of boundary condition. So please be careful about the boundary condition types and number of boundary conditions. This is easy when you are dealing with less than 10 boundary conditions, but believe me, if you're dealing with 20, 30, 40 boundary conditions, which happens a lot in basically it happens a lot in complex problems, you have to be very careful with this. There are other also considerations for proper boundary specification. There are many of them which you will learn as we proceed with our examples throughout the semester, but I just want to mention, before moving on from this subject, I just want to mention one important one, which is the relation, or better to say, the direction of velocity inlet with respect to your inlet boundary condition. The ideal case scenario is that the vector of velocity at the inlet is perpendicular to the velocity inlet boundary. That's the best case scenario. As you deviate from this case, the worst case scenario is that your velocity inlet vector is parallel to the geometry of the velocity inlet. That makes the solution near impossible to converge. Okay, and you can imagine there are cases between these two, from the ideal case to the worst case scenario. But as a rule of thumb, please always try to have your velocity vector perpendicular to your boundary condition at the inlet. Before moving on from our boundary conditions, the last type of boundary condition that we have to discuss is cell zone conditions. So basically, the cell zone conditions are the conditions that are per se not boundary conditions, but whereas they are attributes, characteristics that you need to provide for basically a collection of cells inside your domain. For example, you want to have you have a tank and you want to provide a constant velocity to all the cells at a location, at a smaller volume inside your tank. You do that through cell zone condition. Or another example, you have three different materials in your tank, and you want to define materials in each part of the tank. So you divide your tank to different cell zones and assign different boundary conditions to that cell, to that different zone conditions, different material types to those zones. So look at the cell zones as basically a collection of cells that you can provide a specific characteristics to them. This characteristic could be temperature, could be velocity, could be material type, and could be anything else. Now that we have talked about almost all of the common and conventional type of boundary conditions, before moving on to our next subject, we actually have to talk about one boundary condition that is mentioned here, which are internal boundaries, and for which wall also could be one of the internal boundaries, but the one that I wanted to focus as the last subject in boundary conditions is the interior boundary condition. So what the interior is, it is basically not a boundary condition, and it is what we call a procedure that your software uses. So the way the ANSYS solves a control volume for unknowns is that it assumes everything is a boundary condition. That might seem strange, but that's the best and most optimized way of going through the numerical simulation for ANSYS. So what it does is you provide your conventional boundary conditions, whatever it is, to the cells. So the cells at the boundaries are already assigned some sort of boundary condition. But you also have many cells inside your control volume that you basically want to solve for unknowns in those cells, right? You want to find out the velocities, temperature, and pressure for those cells. What the software does, basically the software assigns all those cells as interior boundary condition. The interior boundary condition is just called a boundary condition. It is not a boundary condition in the sense that you do not need to provide any information for them because you do not have any information for them. They are all the cells inside your domain that you are basically solving your simulation for it. So have this in mind. You don't need to assign interior boundary condition. You don't need to do anything for it. But you will see as we go to our simulation, once we provide all the boundary condition, always and always there is an extra boundary condition that we didn't create, which is called interior boundary condition. Have in mind that interior boundary condition are all the cells inside your domain that you want to solve for unknowns for them. Now that we basically covered our boundary conditions, and I know there are many information to absorb in here, but no worries with that because we will be using these boundary conditions literally in every single workshop, in every single exercise we do in this class. So you will be getting very familiar with them. Now the next part of our discussion, which is rather a short discussion, is the flow classifications. Once we discuss flow classifications, basically theoretically speaking, you will be able to perform simple simulations. What the simple simulation is? A simulation which is laminar, which is doesn't have temperature, which doesn't have turbulence, nothing else. Just simple laminar incompressible flow. So what are the flow classifications? If we go back to our Navier-Stokes equation, and guys, if you recall, when we were discussing about Navier-Stokes equations, I told you that the equation is a very long and complex equation, and I do not expect you to basically memorize this equation. There's no point of memorizing this equation. But I told you what I want you from what I want from you guys is basically to understand what are the involving forces, what are the forces that are included in your Navier-Stokes equation. And here it is what we mean by flow classification. So if you look at this equation, which is your Navier-Stokes equation, as you can probably recall, we had 4 major forces in our Navier-Stokes equation. And just to remind you, if you have forgotten, Navier-Stokes equation is the converted format of F equal to ma. So all we are solving is F equal to ma. But of course, which is in a format which is repurposed for fluid systems. So in Navier-Stokes equation, you're basically dealing with four forces: the local acceleration, which deals with the time; the convective acceleration, which deals with the moment of your system, momentum of your system, sorry. Then pressure gradient, of course, pressure changes in your system, and the viscous forces. Now, using these four categories of forces, and since we know Navier-Stokes is the major equation we are solving, we will classify our solutions, meaning we will classify different scenarios based on which forces are important and which forces are negligible. This is very important once we are going to the simulation. So before performing a simulation, you gotta have some sort of idea what flow classification you are dealing with. For example, if you have a pipe flow which is steady and laminar, since it's steady, you don't have time dependency, and since it's laminar, which means the velocity is very slow, this term is also negligible. So the only two terms you are solving are the pressure and the viscous forces. And as you can see here, there are many different classifications. This is very important to know, because if you recall, I told you as in our I think governing equation session, as we are getting into more complex and more complex problems, just these 5 equations won't be enough, and we would need auxiliary equation to help us solve it. So these flow classifications basically will help us to understand, to know what auxiliary equations we require. So before starting to perform any simulation, you gotta answer some basic questions. These basic questions basically will help you to understand what you are dealing with, and will help you to employ any auxiliary equation if necessary. Okay, so let's start to see what those questions are. You gotta answer whether the flow is laminar or turbulent. That's important. We will cover turbulent flow in one full session. But in turbulent flow, the fluid particles move in a chaotic fashion, whereas in laminar flow, they move in a smooth, layered fashion. So that's one thing. You gotta know if the flow is laminar or turbulent. Second, you gotta know if the flow is steady or unsteady. This is also important, because you wanna know if you have to consider for a transient flow, time-dependent flow, or no, it's just a steady, time-independent flow. You gotta decide, rather than saying decide, you gotta determine whether your flow is incompressible or compressible. This is very important, because if the flow is incompressible, you're dealing with other sort of equations rather than the compressible flow. For starters, what we discussed, if you have incompressible flow, your inlet boundary conditions become velocity inlet. Whereas if you are dealing with compressible flow, it becomes mass flow inlet. You gotta decide, or you gotta determine whether you are dealing with single phase flow or multi-phase flow. This is very important. We do not cover multi-phase flow in this class, which is being covered in our more advanced course MI 1214, which is a graduate level course. But nonetheless, you have to know whether it's single phase or multi-phase, because if it is a single phase, which is you're dealing with one phase, either liquid, either gas, without any phase change, you do not basically need any auxiliary equation for that part. But whereas if you're dealing with multi-phase flows, meaning you're dealing with liquid and solid, liquid and gas, gas and solid, or even all three, liquid, solid, and gas. So if you're dealing with multi-phase flow, the whole scenario for solving the equation changes. Basically, what will happen is you need some more auxiliary equations to be able to solve it. So this is one of the most important things that you should know before starting to simulate your control volume. The next question you gotta answer is whether it's a homogeneous or heterogeneous. Homogeneous flow is only one fluid material exists in the fluid flow. Remember, homogeneous is different than single phase. A flow could be single phase, meaning everything is liquid or everything is gas. But homogeneous means it could be water and oil, asphalt and honey, so on and so forth, right? You have different materials. So if you have one single material, no matter what the phase is, because it could be homogeneous multi-phase. For example, you have only water, which means it is homogeneous, but it could be multi-phase because you have water liquid and water vapor. So homogeneous and heterogeneous basically deals with the number of materials, different materials in your system, whereas single phase or multi-phase deals with the state of the flow that you are in. The next part is, which is very important part, is basically whether my flow is Newtonian or non-Newtonian. If the flow is Newtonian, basically like water, air, or many of the other things that you are dealing with, the viscosity of your system doesn't change by anything. You have constant viscosity like water. But there are many materials that basically their viscosity changes with different parameters. For example, asphalt. The viscosity of asphalt changes by temperature. As you increase the temperature, and you have seen this in many places, as you increase the temperature, the viscosity of asphalt goes down. It becomes more liquid. But whereas as you decrease the temperature, the viscosity of asphalt increases, meaning it behaves more like a solid. Or another example, honey or toothpaste, which they are both similar. Their viscosity changes by the force you're applying to them. Meaning as you increase the shear force on these liquids, the viscosity decreases. Okay? For example, you see honey dripping from your spoon. As it drips more and more and it gets elongated, it can flow easily. So as the force gets larger and larger on your, as the shear force gets larger and larger on your material, in the case of honey or toothpaste, the viscosity goes down. So this is another question you gotta answer, whether the flow is Newtonian or non-Newtonian. And here you can see many examples of different types of material that they behave in a various ways, responding to the forces or temperature being applied on them. So there are other considerations other than basically other consideration other than these questions that you have to answer. Most importantly, the Reynolds number. Always and always calculate Reynolds number, even if you're not asked to do, because Reynolds number determines many things. It determines, other than, in addition to whether it is laminar or turbulent, it determines other things as well. For example, if your Reynolds number is much larger than 1, your flow is dominated by inertia. Whereas if your Reynolds number is much less than 1, your flow is dominated by viscous forces. So the Reynolds number plays a very important role in your calculation and simulation, and I can certainly say it's one of the most important numbers you will ever be dealing with in CFD. The other consideration, whether it's two-dimensional or three-dimensional, whether it's symmetric or asymmetric. So these are all the conditions, all the questions that you have to answer, and your answers to these questions basically determines what sort of equations, in addition to your 5 basic equations, have to be used to solve for your problem. Now, in order to understand everything better, the example we will be solving for this subject is a steady laminar flow inside a pipe. It's a very simple problem, but it will give you an overview of what we discussed, and also it would be an introduction to simulation. So that would be our simulation, which is our first simulation. Please make sure you have access to the remote if you're working remotely, in order to be able to perform the simulation.